In this video, I want to talk about a special case that you may encounter when trying to solve circuit using the mesh current method. So let's just take a look at this circuit. We have two independent voltage sources. We have 5 resistors. And also we have this independent current source with the value 5 amps. So let's just try to write the equations based on the mesh current method. So if you look closely, you see that we have 3 meshes here. We have one mesh here, we call it mesh A. Then we have another mesh here, we call it mesh B with current IB. And then finally we have the third mesh, we call it mesh C with the current IC. So based on the mesh current method, now we should be able to write the equations for this circuit using mesh currents and KVL. So let's just do that. For mesh A, what we have is, if we go from, let's say, this point around this mesh clockwise, we have negative 100 volts plus the 3 ohm resistor. What is the net current through the 3 ohm resistor in the direction of IA? So since this 3 ohm is common between mesh A and mesh B, it is going to be IA minus IB. So the net current is IA minus IB because IA is going from left to right, IB is going from right to left. Then we get to this independent current source. If you remember from the earlier lectures, we said that for current sources, we don't know the voltage across them until everything in the circuit is being solved. So because of that, I just assume a voltage polarity like this, positive here, negative here, and I call this voltage to be V. So I simply write it as V. And then we get to this 6 ohm, which only has IA going through it. So we have 6 IA equals 0. So that is the KVL for mesh A. What is the KVL for mesh B? If I start from this point, we have 10 IB plus this 2 ohm, we have 2 multiplied by IB minus IC. Again, the net current that goes through this 2 ohm in the direction of IB. So, since IB and IC are in opposite directions, we have IB minus IC. And then we get to this 3 ohm resistor. So this one is for mesh B. We have 3 multiplied by IB minus IA. The net current that goes through this 3 ohm resistor in the direction of IB. Finally, for mesh C, let's start from this point. Again, we have this current source in the mesh. So since we cannot know its voltage until everything in the circuit is being solved, so I just simply put it as V. So since we are going from the negative side of it and following the passive sign convention, I have negative V here. Then we have the 2 ohm. So the net current going through the 2 ohm in the direction of IC is going to be IC minus IB. Then we have this 50 volt voltage source. So we have positive 50 since we are entering from the direction of the voltage drop. And then finally we have 4 multiplied by IC because it is not common between 2 meshes, only IC goes through it. So that is equal to 0. So now we have 3 meshes. and we have three equations. But we have four unknowns here. So this voltage for the independent current source that we have here is not known. So how can we basically eliminate that? Because we said that until everything else in the circuit is solved, we cannot know the voltage across this current source. So what we can do is that we can find the addition or summation of equations for mesh A and mesh C. So let's just do that. We have negative 100 plus 3IB minus, IA minus IB plus V plus 6IA plus negative V plus 2 IC minus IB plus 50 plus 4 IC equals 0. So now, as you can see, we have V with the positive sign, and also we have V with the negative sign. So these two would cancel each other out. So the end result is going to be negative 100 plus 3 IA minus IB plus 6 IA plus 2 IC minus IB plus 50 plus 4 IC equal 0. So we had equation B, which was only based on IA, IB, and IC. So this is the first equation that we can use to solve the linear system. Now we have a second equation that is only based on IA, IB, and IC. But we need three equations. So how can we come up with the third equation? The third equation can be acquired based on the fact that this current source is common between mesh A and mesh C. So if you look closely, you see that the direction of this current source is in the direction of IC, right? It is going clockwise. So because of that, we can have IC minus IA to be equal to 5 amps. And this will be the third equation that we need to write in order to be able to solve this circuit. So what if we want to get rid of this intermediate step? That's when I'm going to introduce the concept of a super mesh. So when we have a current source that is common between two meshes, we can combine those two meshes into a super mesh. So if I conceptually eliminate this current source, I can say we have this larger super mesh here. And then we write the KVL for this super mesh. So for this super mesh, let's say we start from this point. We go from the negative side of the voltage source. So we have negative 100 in this direction. Now we get to the 3 ohm. So the 3 ohm resistor is common between mesh A and mesh B. So that means that the current in the direction of IA is going to be 3 multiplied by IA minus IB. So this is what we have. Then we get to this 2 ohm. We have IC going in the direction of the super mesh, but IB in the opposite direction. So what is the net current in the direction of the super mesh or in the direction of IC? It's going to be 2 IC minus IB. Then we get to the positive side of this independent voltage source. So we have positive 50 here. Then we get to this 4 ohm resistor, which only has IC going through it. So we have 4 IC. And then we get to this 6 ohm, which only has IA going through it. We have 6 IA. So if we reduce this equation, if we basically factor out all the common parts, this is the equation that we get to. And this is practically the same equation that I calculated in the previous slide. So using the concept of super mesh, you can eliminate that intermediate step. But all the rest are still the same. So you still need the KVL in mesh B. You still need the relationship between IA, IC and this 5 amps. So you still need IC minus IA equals 5 amps. But to get to this equation, you have to go through fewer steps. And that is by using the concept of super mesh. So in this video, we went over a special case of mesh current method. And that was the case where we have a current source that is shared between 2 meshes. So we said that we can combine those 2 meshes and create a super mesh, and then we write the KVL in that super mesh. That can help us reduce some of the intermediate steps that we need to take in order to solve a circuit using the mesh current method.